Next up, I believe we have Junehyoung. Jeon from University of Texas at Austin is going to tell us about emerging black holes, mass function, high-redshift universe. So I'm going to give you 12 minutes, and then I'll give you a 3-minute warning and a 1-minute warning with the comments.
Hi, I'm Junehyoung. I'm a grad student at UT Austin. I'll tell you about this work, mostly based on the paper of the same title. And you can see my collaborators listed here. Some of them are in the room as well. Yeah. So the question, question that has been long since astronomy is the presence of these massive black holes at early times. We see these massive quasars at high redshifts, and also with JWST now even up to redshift 10, where these massive black holes have been observed, and it's we don't exactly know how they could be so massive, so early on. You know, the standard, established pathway for black hole formation is this stellar remnants formed at low masses, but then they have to grow by quite a large number, order of magnitudes, to become these extremely high mass black holes. So we have to invoke some exotic models, such as superheating accretion, where the black holes grow much more rapidly, or this heavy seed scenario, where the black holes form initially very massive early on, so that they have an easier time to these high masses. As Dale mentioned, there's also these problem of overmassive black holes, where we see all these black hole cell mass ratios being much higher than what has been established locally. So this would indicate that the black holes formed before the stellar population could actually have evolved. So in this case as well, either the black holes evolved very quickly to beyond the stellar masses, or they just formed very massive early on before the stellar mass could form. And of course, we have the little red dots, which we believe they're Asian, but we aren't exactly sure about what they are. But one question is then, these masses could still be reached by these model lines here. If we invoke some extreme models, it's not impossible to reach these masses. And the problem we face, as Dale mentioned, is that what does the universe really do in this case? Since both of these scenarios could do it, how do they distinguish the two cases? So quickly introducing these two scenarios that are considered high redshift, with the stellar remnants. And at high redshift, we expect the stars to be metal-free at the highest redshift, the first top 3 stars. And being metal-free, these top 3 stars are expected to be more massive than the local stars, and so result in 100 solar mass or so of black hole remnants. The heavy seed scenario considered, the main one considered is a direct collapse scenario, where under rare conditions with low metal density, low molecular hydrogen, cooling at low temperatures is effective, so that these massive gas clouds are able to collapse directly into a supermassive star, then soon to a direct collapse black hole of 10 to the 5 solar masses, so at high masses. So in trying to distinguish these two scenarios, we believe we can use the black hole population observations to be able to distinguish these two scenarios. These are observations of the black hole mass function. So per black hole mass spin, what is their number density? And these are different observations. And then we expect these different scenarios for black hole seed formation will result in different characteristics of this black hole mass function. So by examining these black hole mass functions at lower masses and then also at earlier times, we should be able to distinguish the difference, we should be able to tell between what the universe actually does in forming these massive black holes, which of course in population studies, Roman will be ideal to do. And so to make predictions for this black hole mass function, we use a semi-analytical model named A-slot, where we model a galaxy formation on top of a halo merger tree. And I've built a black hole model on top of these A-slot model, which includes black hole formation under different seeding scenarios to test what the differences might arise with the different scenarios. So these are our predictions here. So we test the two main scenarios, the stellar remnants and the heavy direct collapse black hole seeds. And what we find initially is that for the existing constraints that at the time, both models, either heavy seeds or light seeds, could reproduce observations. So this purple line is the stellar remnant scenario. The blue and the red shaded regions are the heavy seed scenarios. And then within reasonable assumptions and free parameter choices, the existing constraints could be satisfied. One major difference you see is this bump from heavy seeds at 10 to the 5 where we see these direct collapse black holes at. But of course, at the time, the observation didn't reach down to such low masses. This green line here is an extreme model where we enforce that every black hole in the universe accretes at super Eddington rates continuously. So this isn't realistic, but we needed this model when you go to higher redshifts. So this is the same black hole mass function, but at redshift 9 to 10, or like 500 million years after the Big Bang, so much closer to the formation, the period of the initial seed formation. And here we do find more differences between the models. There are some observations here, but you shouldn't really trust these y-axis here, since these are all just individual objects. So these upper limits are from just 1 divided by their approximate survey area. So depending on what future observations possibly Roman will bring, all these points could move up or down. We don't really have any constraints on the number density of these massive black holes at these early times. I guess a more important thing is their extreme masses, even at these earliest times. You see that maybe harder to see with this purple region here. The standard light seed model can never reach these extreme black hole masses that observe at high redshift. You either need these massive direct cluster black holes or the extreme model we said earlier where every black hole accretes at super identity rates to reach these extremely high masses. Another caveat is that then these two models aren't really mutually exclusive. The universe could have formed direct cluster black holes, but also maybe in some extreme cases we don't know, supported this extreme growth rates for the black holes to reach these high masses. So we do test some combinations. Yes, where we have our physical models combined with a very small fraction of these extremely rapid growth black holes. And in this case as well, the observations agree well with either the models that include heavy seeds or not. And the most direct way to distinguish these models would be to reach this low mass regime where we expect the heavy seeds to be seeded at and reach this peak, which is of course very difficult. And then we predicted that maybe gravitational lensing should be able to reach these low masses around 10 to the 5 solar masses or so. And surprisingly, after we made our prediction, there was this glimpse survey with the gravitational lensing glimpse survey with JBHT that was able to reach down to around 10 to the 5.5 solar masses or so in the black hole mass function. These are these red points here. They surprisingly find this sudden rise of the black hole number density at low masses, which agreed well with our heavy seed predictions. So this could be one initial indication of the existence of heavy seeds, but still, this is just one point here. We would like even lower masses if possible, and then also more point gravitational lensing surveys to reach these low masses at high redshifts. But of course, with lensing, it's difficult, and then also with lensing, we're limited by the volume. Since lensing gravitational lensing is small, we're with much smaller volumes, and then it's difficult to get number densities out of them. An alternative pathway, I guess more indirect pathway to distinguish the seeding scenario is to go to higher redshifts. And this is another, again, the combination model at high redshifts. And I put a rough prediction of the lowest mass black holes that Roman could reach at these era. I believe there are more talks later on that will discuss more on how Roman could reach, what a black hole mass or black holes that Roman could reach. And then in this case, we believe the Roman will have distinguishing power to indirectly say what the accreting black hole models are. So since there's no constraints, strong constraints at high redshift, all he can do is just change the number of these, how they're accreting black holes. So since at redshift 9 to 10, this is soon after the initial formation of the black holes, not too long after the initial formation of black holes, this amplitude of the black hole mass function is very sensitive to how many black holes are able to be accrete very efficiently. So you see that by changing the percentage of these efficiently accreting black holes, the amplitude of this black hole mass changes, which Roman could probe. So we don't know yet what Roman will bring, but let's say if Roman observes an overabundance of these massive black holes at high redshifts, then we expect that the universe will be able to support these extreme growth rates, however that may be. In contrast, if we find a dearth of black holes, of massive black holes at high redshift, maybe around this GNZ11 constraint right now, it's much lower than all these existing lines, then we expect that the universe be very unsupportive of these extreme math growths, that the universe won't be able to very efficiently sustain these efficiently spreading thin growth rates, and maybe it's more of the heavy seeds, these rare extreme cases to produce these massive black holes, but also at extremely low number. So depending on what the future observations might bring, which will tell us on the formation rates, on the formation pathways for these massive supermassive black holes. There are other constraints beyond the black mass function. This is the distribution from our model to the distribution of the black hole to star mass ratios across redshifts. And this is the subtle remnant model here, the class black hole model here. And obviously, we do see this difference between the overmassive populations between the scenarios, where we see this small population of these overmassive systems if direct class black holes should form in the universe. Of course, we can enforce superadic accretion to have the stellar remnants also produce these extremely overmassive systems. But again, depending on how well the universe supports these extreme systems, the number density of these overmassive systems will change, which also Roman could probe at earliest times and then tell us on what the universe actually does. A different constraint is also on the metallicity. So in this case, this is a stellar mass black hole to stellar mass ratio versus the average metallicity of our systems. And the stellar remnants have a difficulty producing both overmassive and metal-poor systems, such as this QS1 system here, since by definition the stellar remnants form within stellar environments that are already metal-enriched, while direct collapse black holes by their design form in metal-poor systems and with very low stellar masses can form these like overmassive and also metal-poor systems. And as a quick aside with the LRDs, using our same metals, we wrote a paper that argued for the direct collapse black holes matching the population statistics of LRDs more. It's like the LRD number density versus our direct collapse black hole model. And being more rare than the stellar remnants, could better match these LRD number densities and other population statistics. But by constraining the formation pathways, these models are also all based on this constraint at redshift 5 to 6 at lower redshifts. If we are able to better constrain these pathways for black hole formation at the highest redshifts, we also may be able to tell what the black holes do, how these LRDs may form should they come from the different seeding scenarios for supermassive black holes and AGN as well. So I'll leave my conclusion slide here. So the one question we want to address is how these quasars, these massive black holes form at the earliest times, how the universe forms them. And while it may be difficult to reach these low masses at the extremely high redshifts directly, Roman could help us probe the population statistics of these earliest times, of these massive black holes at the earliest times, which give us strong clues on how the universe formed or how efficiently black holes are able to grow at high redshifts, and what are the seeding channels for these extreme cases are. Thank you.
Any questions for the?
So are you saying that the current Roman surveys can yield some power in distinguishing these high redshift supermassives, or would you have to do a deeper survey or add the K-band or do something else to give you the leverage that you need for these 10 to the 7th solar mass?
Yeah, I think deeper surveys would be better, but I think even with the current surveys, I believe like these predictions are for nitrogen 5 or like magnesium 2 lines, so non-Balmer lines. So I think these could be reached even with the existing surveys. Yeah, in the deep surveys, yes. I guess we actually don't know how well it will do until the observation come in, but these are like the rough predictions based on the current survey limits. But of course, if we have to go deeper, it'll be better.
So I guess one caution or caveat, or maybe just thought about the way we present this and try and test these is I think it might be useful to, instead of phrasing this as sort of direct collapse or heavy seed versus light seed, to think about this as sort of rapid intermittent accretion versus slow extended accretion, because most of the super Eddington models actually, when people really model super Eddington accretion, they predict that most of the growth is dominated by very short phases, much less than 1 million years, where you might accrete at 100 or 1,000 times the Eddington limit, which is really what a direct collapse is, just an extreme example of that, right? It's all in one burst. And I think all of those, my question is, I think all of those would look like your heavy seed model in some sense, whereas what differentiates the light seed model is really that the accretion it might be super Eddington, but it's a modest super Eddington that's extended over a long period of time, like 10 to the 8 years or something like that. Is that correct?
Kind of. If I go back to the models here, like all these models besides the green line is like intermittent models, since like based on some halo properties, we have some bonding hole accretion rates onto these black holes. So these grow at, like, as you said, in different rapid phases of higher accretion rates. But then why we had this like extreme case where this one is continuous accretion is that if we didn't have that, then the stellar remnants could never reach these high masses under, of course, under our assumption of the Bondi hole accretion rate. So we needed continuous accretion, at least for the stellar remnants, to reach these high masses. So we invoke this model, but of course, there are assumptions to go into our growth models here. So I think if we boost the Bondi hole accretion rate or something, maybe these intermediate growth rates onto stellar remnants could also grow these. But besides this green model, everything is like non-continuous accretion.
All right, I think we need to move on to the next speaker, so let's thank this one.